Now more on electric potentials, and this time focusing on how they relate to electric field. One big idea is that we can picture electric potentials with so-called equipotential lines, and they are just like the word says, a set of points that are all at the same electric potential. And ordinarily when we draw them, just like in the book, we draw them with dotted lines to distinguish them from electric field lines, which are solid lines. And we label them with the value of electric potential that all those points have. And when we draw a series of equipotential lines, whenever we skip from one line to the next one to the next one, the change in potential is always the same. That makes it easier to interpret the equipotential line. So 20 to 10 to 0 to minus 10. Every time we move from the upper left towards the lower right, every time we move from one equipotential line to the next, we're always dropping by the same number of volts, 10 volts in this case. The other important idea, you read about it a little bit in the text, is this relationship between electric field and a change in electric potential between different locations. Magnitude of the electric field in some region of space is equal to the difference in potential between 2 points in that area divided by the distance between those 2 points that have that much potential difference. One really important thing to notice here is that whenever there is a potential difference, in other words, that potential difference is not zero, whenever there are different potentials at different points, then you'll always get an electric field. Or it works the other way too. If there is electric field, there will always be different potentials at different points. For example, here, the electric potential is different at all these points from what it is here, and different here, and different here, so that there is a potential difference, 10 volts, potential difference of 10 volts, and the distance you have to go to get that 10 volt potential difference is just from here to here. Let's say that distance is 1 centimeter. So that means in this region here, the strength of the electric field is just a 10 volt potential difference, delta V, and going from here to here was a decrease in potential. So actually, in that case, the delta V in going from here to here was negative, a negative change, a decrease, but we're only interested in absolute values and sizes here. And you divide by the distance between the 2 points that are 10 volts apart. That distance was 1 centimeter, or 10 to the minus 2 meters. And that means you've got an electric field strength of 1,000, or 10 to the 3. 10 to the 3 watt volts per meter. We've seen before that a good unit label for electric field is newtons per coulomb. Well, another perfectly good unit label for electric field is also volts per meter. They mean the same thing. You could use either one. Now think about this in a little more detail. If we get a certain amount of potential change over a really, really short distance, then its potential change over a small value of d, the denominator is small, so the fraction is big, so this is large. Large, strong electric field. Whenever potential changes rapidly or changes when you just move a very short distance, small d. Or a potential change over a long distance, on the other hand, if you have to travel a long distance d to get that same amount of potential change, then this is much bigger, field is much smaller. Small electric field, where the potential is changing much more slowly as you move from one point to another. Just show that with some pictures here. But first, before I draw the pictures, there's one other big idea that I need to mention. This is one of the big ideas. And then the other one goes like this. Okay, excuse me, had to find the eraser. The other big idea is this, that the electric field will always be perpendicular to a field, to an equipotential line. Or to put it another way, wherever an electric field line and an equipotential line cross, they must cross perpendicularly. So there's an equipotential line, and if there are some electric field lines also in this space, then they must cross this line perpendicularly. Think for a minute about why that has to be the case. And the reason it has to be the case is related to this big idea here. Here's an equipotential line, and that means if you pick any 2 points on that line, let's say this one and this one, there is zero potential difference between those 2 points. Zero potential difference between those 2 points. Zero potential difference means no electric field. That is, there's no electric field between those 2 points. And of course, there's nothing special about these 2 points. You could pick any 2 points along the equipotential line and then use the same argument to show that there's zero electric field between those two points. In other words, there is no electric field ever along an equipotential line, which means you can't have an electric field like this. The electric field like this would have a component along the equipotential line. You could divide up this electric field vector into a component that's parallel to the electric field line. Call it E parallel. And then a component that's perpendicular to the field line. But because there is zero potential difference between these 2 points, there is zero electric field between those 2 points. So this component of electric field along the direction of along the equipotential line cannot happen. A component of electric field like this must always be zero. In other words, only fields that are perpendicular to the equipotential line can exist. Basically because of this. So electric field always perpendicular to an equipotential line. And let's see what that looks like pictorially. I just start with the simplest possible case where the electric field is uniform throughout some region. That is, the electric field has the same value everywhere and it's pointing in the same direction everywhere. And you'd represent that by electric field lines that are straight and all pointing in the same direction. And evenly spaced. Right. Evenly spaced tells you what? Well, it tells you this. As you move from here to here, the field lines don't get closer together, which means you're not moving to a region of stronger field. Remember, when field lines are closer together, that indicates stronger field. And as you move from left to right, the field lines are not spreading farther apart. Spreading farther apart indicates weaker field, but since they're not spreading farther apart, the field is not getting weaker. They're not getting closer together as you move left to right, so field is not getting stronger. They're not spreading apart as you move left to right, so the field is not getting weaker. Well, if the field isn't getting bigger and it isn't getting smaller, the only other possibility is field is maintaining the same strength everywhere, indicated by even spacing everywhere. And the lines are all pointing in the same direction, indicating that everywhere you look, the field will point in the same direction. Okay, so electric field lines and equipotential lines are perpendicular. So in this region of space, there is electric field, which means there are potential differences between points. So you could draw a bunch of equipotential lines representing different potentials. But remember, equipotential lines are always perpendicular to the field. So in this case, the equipotential lines would have to be perpendicular to the field lines. In other words, the equipotential lines are just plain vertical in this case. And remember, from one equipotential line to the next, to the next, to the next is always the same amount of potential change. So let's say here it's 5 volts and 0 volts and minus 5 volts and minus 10 volts. Decreasing by 5 volts every time we take a step to the right. But from here to here, you get a 5 volt potential change in this much distance. From here to here, you get a 5 volt potential change in the same distance. So whether you're looking at this or this, the delta V is the same, and the distance you travel to get that 5 volts of potential change is the same. And then here, you travel the same distance to get another 5 volt potential change. So 5 volt potential change, always same distance, always. It corresponds with the electric field having the same magnitude, always. Or to put it another way, if the electric field is constant, the equipotential lines are evenly spaced. If the electric field is constant, the electric field lines are equally spaced everywhere, and the equipotential lines are equally spaced everywhere. Now let's make it a little more complicated. Let's say we've got a set of equipotential lines like this. So, let's say here the potential for all these points is, let's say, 20 volts, and here it's 15 volts, and here it's 10 volts, and here it's 5 volts, and here it's 0 volts, and here it's negative 5 volts. Nothing wrong with having negative values for potential. And you can see that here to here and here to here, you get exactly the same spacing, the same distance for each 5-volt potential change. So delta V of 5 here and delta V of 5 here, and the same distance here and here. So this quotient is the same here and here. So the value of electric, or the magnitude of electric field, is the same everywhere around here. But now here, for the same 5-volt potential change, you get that 5-volt potential change over a much shorter distance. Smaller d for the same delta V. Numerator stays the same, but the denominator gets smaller, so the fraction gets bigger. That corresponds to a stronger electric field. So the electric field here is stronger than it was here. And you indicate stronger electric field by having field lines closer together. So field lines would look something like this. Remember, field lines always have to be perpendicular to equipotential lines. But somewhere in here, the strength of the electric field is changing, so that by the time you get to this region, the electric field is stronger. And you indicate that by field lines closer together. So something like that. But again, wherever we have drawn equipotential lines, you have to draw the field lines perpendicular to them. Now, one more example. Let's just imagine the simplest kind of electric field, the electric field caused by just one lump of charge, and we'll say it's positive charge. In that case, we know, remember, electric field points in the direction of the force on a positive charge. If you put a positive charge anywhere, it'll feel a repulsive force from this positive charge. So a force on a positive charge here would point straight away, this radiate straight out from the source charge here. So electric field lines radiate straight away from that one lump of positive charge. And equipotential lines have to be perpendicular to field lines. But the way it works, if you think of these as radii of a circle. Radii are always perpendicular to the circle itself. So in other words, the equipotential lines have to be circles centered on the source charge. So then that distance there is a radius of the circle, and when we say that the circle is perpendicular to the radius, what we really mean is that a tangent line parallel to the circle at that point is perpendicular to the radius, and a straight tangent line tangent to the circle at this point is perpendicular to the radius, and a straight tangent line tangent to the circle at this point is perpendicular to the circle, and so forth. So concentric circles around that source. Well, we know that the electric field from one lump of charge is stronger when you're close to the source, and weaker when you're farther away from the source, and that's indicated by the field lines. The field lines are all closer together, close to the source, which indicates stronger field, and the field lines are spread farther apart when you're farther away from the source. Field lines farther apart indicates weaker field. And a similar sort of thing would have to happen with the equipotential lines, because if the electric field gets weaker, then for any given amount of potential change, this must be getting bigger. Right? When the field gets weaker, let's say this is a 5-volt potential change, if this is getting weaker, this is always 5 volts, then you have to travel a greater and greater distance to get to that 5-volt, to get that 5-volt potential change when the field is getting weaker. So as you go farther and farther away, as you go to regions that have weaker and weaker electric field, smaller electric field means you have to travel a bigger distance to get the same potential change that you had before. So let's say that this, all the points on this circle are, let's say, 100 volts, and all the points on this circle are at 80 volts. Then now to get another 20 volt change in potential, you have to go a greater distance here than you did here, because out here the field is weaker. Everything else that we do is just an application of those ideas, and those ideas will come up especially and quite often when we think about electric current and how electric current is produced.